So before we really get going, I gave you a little bit too little to do last week. Probably for some of you that are comfortable in installing software and getting it up and running and all that. Prior, I've had students that, for one reason or another, had problems getting software installed and running. I kind of didn't want too much, although I was hoping that you guys got a chance to work through some of those, just so you got RStudio up and running and just tried it out a little bit. It is somewhat touchy, weird. I mean, the syntax is really what, if any of you have done programming, and I know several of you have, the syntax is actually based on 40-year-old ideas. It kind of sounds weird, but R as a program comes from a prior product or prior program called S. S was developed at Bell Labs. And because it was developed at Bell Labs with support from the government, it was released to the public domain. And then S was implemented in a commercial version by a company up in Washington, and they released it as S+. And did some modifications, because I don't know how much of this history you care about, but Bell Labs, eventually, the Bell got broken up and all that, so there was no more Bell Labs, and S was just kind of floundering out there. It got picked up, made a commercial version of it. But we're still talking about stuff that happened, that was developed in the 80s, late 80s, early 90s. I remember being at the University of Oregon Computing Center working as a statistical programmer in 1990, where I got the responsibility to support S+. So it's at least that old. And that shows up in the quirky syntax. But the idea, and then what happened was eventually, since S was in a public domain, and it's targeted for the kind of analytics computations that we typically do, I mean, that's really what it was designed to do, then there were some academians started to, when open source become more interesting or more feasible, I think it might be a better word, then they started to develop this version of S or R as an open source project. That kind of started up in the mid 1990s. It was very, very premature and kind of really low, really just a small community through the 90s. Kind of took off a little bit more as both the tools and the infrastructure and the computers got better. And then R kind of got better and better, and towards mid, and you kind of got into the first, 2005, 2006, you got this effect of computers, multi-core, Linux, development environments, and all that kind of stuff that all of the other open source products benefited from. It also benefited R. And so R became, and then what happened was, and this is a little bit of an interesting history for me. It may or may not be too interesting for you, but up until about 2000 or 2002, 3, 4, if you wanted anything kind of done sophisticated statistics, you had to buy SAS or SPSS or something like, well, there are some other ones that don't exist anymore called Systat, BMDP, and some other ones that were commercial packages, and they were expensive. They were really expensive because they were considered very niche products, heavy development costs associated with them. By 2004, 2005, R started to be so good that it started to overtake some of these commercial packages. Not only that, but R allowed typically professors in academic institutions or doctoral students and all that wanted to develop new techniques and new tools, they could do that in R very easy. You could not easily hook something into SAS or SPSS or any of these other ones. You could easily hook it into R. So R became a playground, so to speak, development environment, analytical development environment for a lot of new techniques. And that has continued. So very often now, if there are new techniques developed, they will first be developed in R. May not always be the most efficient environment, but that has become typically the bleeding edge of what's available. So that's part of the reason now for R being as popular as it is. The other thing that I think has helped R is R used to, and still basically wants to keep all its data in memory. Now, for those of you that know a little bit about computers, we go back 10 years and you loaded everything in memory and there wasn't that much memory, relatively speaking. So R was severely constrained by having to work only within the RAM available, the memory available. Now, I mean, you probably all have at least 4 gigabytes, maybe 8. Starting to be okay to have 16 gigs when you get 64-bit systems. So now you can suddenly load in and work with data sets in R that used to be unfeasible. You couldn't do it. The other thing that R has benefited from, as most of the other open source, is the whole multiple cores, multiple CPUs, parallel processing functionality. So with all of that, then we will use R and a fairly fundamental, trying to keep it easy, but it gives you a taste of what an programmatic analytical environment can do for us. It's a different way of approaching things compared with Excel. To some degree, it's also different, but different in a different manner, if that makes sense, from Tableau. Tableau does some things really, really, really well, but the moment you start to want to do the kind of things that we're going to look for the second half of the class, Tableau kind of falls over. It's not designed for that. Tableau is designed for building nice graphical views or dashboards or interactive graphical analytics, not really to do the modeling that we eventually will get better and better at. That said, last week we touched a little bit on just what I think I call correlation analysis. We'll kind of revisit that a little bit, but now overlay correlation analysis with what we call linear regression. And talk about regression analysis, kind of broadly what it is. Start, and most of the time we're going to spend today is going to be simple linear regression. Eventually, next week, maybe we'll touch on this today, but next week, multiple linear regression, and we'll start talking about what it means to build good regression models. And this is, if you get this approach, if you understand kind of the flow, then you will, I think, enjoy and appreciate a lot of what we will be doing in the next year and a half. So, what is regression analysis? Well, one of the key things is what we've talked about before, is you have a dependent variable that you want to understand better, or you want to be able to predict, or you want to model a dependent variable. And then you want to explain that dependent variable using one or more independent variables or predictor variables. Now, normally we'll say, we go left to right when we think about things. In this context, because the way we're going to write up these kinds of models, it's typically going to be y equals something like beta 0 plus beta 1 x 1. This is a very, very simple model. What it says is that y, our dependent variable, equals b0 being an intercept term, and then a coefficient times our independent variable, our predictor variable. Very fundamental. This is the equation for a straight line in an XY plot. Hope you guys recall enough of your basic math to recognize what I'm talking about. Cross my fingers and hope, right? So just to make 100% sure, typically we'll label the vertical axis y. This is kind of like, this is how statisticians and modelers do it. It's just by definition, this one. Then the horizontal is x. And this line is basically, in this case, the straight line. And here's where the linear comes in, linear line, where B0, this value right here, that's B0. And B1 is basically the coefficient that tells you how much it rises for each unit of x. Am I? Okay. There actually is an implicit adjustment here. I might as well mention it. See if we can do this. Plus B1 x1. There is an implicit x0 here. X0 is always equals to 1, but it is there. This you may or may not later on get into this. This becomes important if you end up writing these kind of formulas in matrix form. And you may or may not ever kind of get there, but being aware that there is actually an implicit x0 in here can later on be important for you. For now, it's not a big deal, but it is there. If any of you have kind of played around more with math, you might have come across this before. It's not really that big a deal, but so this is a very basic, simple linear regression, single independent variable, single x basically. Now, if we extend it to multiple linear regression, we just add x's. What happens is a simple linear regression we could easily plot in this xy plot, right? What happens when you get 2 or 3 or 4 or 17 or 24 x's? The plotting becomes interesting. Most of us can't really comprehend more than, we might be able to go to 3 dimensions where this line becomes a plane. But when we get to 4 and 5 and 6 dimensions, plotting doesn't work anymore. You basically have to work with the numbers. However, if you understand what's going on here, and we will go over that, then it extends cleanly. It extends fairly straightforward to the more x variables. Adding more x variables doesn't really change the overall flow of the model. So that's why I'm saying, if you get what's going on here and what we're going to talk about today, then the rest is just kind of tweaking, almost. So simple linear regression finds a linear relationship between one independent variable x and one dependent variable y. Sometimes we also will call these x's a predictor variable. Depends a little bit on context. When we start out, recommend first prepare a scatter plot, an XY plot, to verify the data has a linear trend. Remember we talked about this last time? Linear trend basically, does it look like we have a straight line in here? Then regression, linear regression works. If we have nonlinear or curvilinear, or basically no relationship, if it's no relationship, it doesn't matter what we do. But if you have curvilinear or other kind, if it looks like might be an S in there, there might be something like this, it might be, then alternative approaches. There are tricks we can do mathematically, and there are other kinds of models. But we will start out with, looking for linear relationships. So far, so good? So, here is a data set. It's a fairly straightforward data set. You might recall it from 120, the whole market value data set. This is actually, I read it into R. And it contains 3 variables. We're really going to only look at 2 of them. But the idea is that market value for a house is typically related to the size and the square footage. Agreed? Okay. Hold that thought, because it turns out to be really, really important. Eventually, you're going to get data sets where there will be variables in the data set that may or may not have anything to do with the dependent variable. But if you just, arbitrarily or just for efficiency purposes, throw all the data into the model, computer will happily compute garbage. Case in point. Here's a data set that you probably will end up working with about fuel economy, trying to predict mileage, highway mileage or city mileage, based on different characteristics of an automobile. Well, in that data set, there are a number of variables. One of the variables is an engine ID. It's a number basically assigned to the engine by whatever department that does this fuel economy data. It's a number. We've had students use that as a predictor variable. Do you think an arbitrarily assigned engine ID has any predictive value for mileage, fuel, miles per gallon? There is no relevant connection. There is no kind of logic in how an arbitrary value can help you predict MPG. But the computer will happily do it because it's a number. So it will compute. But here is where the reason I asked here was, does it make sense logically? We need to make sure you know the data well enough that not only can you do it technically, but you can also understand conceptually. There's another part to this, and that is What if we flip these around? Remember, we can do correlation analysis. We get X with Y or Y with X. It doesn't really matter, right? However, now we're doing modeling. Now it matters which one is the Y and which one is the X or the predictor. Now, computer will happily say, oh, size or square footage as a dependent variable can be predicted by house price. Does that make sense? You know, what precedes what?
Square footage, right?
Yeah, I mean, square footage is a better predictor of house price. There is a reasonable relationship there. If it were the other way, you know, the best way to get a bigger house was you just upped the sales price. And suddenly the house was supposed to expand. If that relationship was true. Or it's a little bit like, we talked about that, remember the body weight and heart weight of cats? Okay? It's like, which one depends on which? Like, if you pump up the heart, that doesn't necessarily make the cat bigger. So, what we have here is we say X square footage, that's the predictor. Y is the market value in dollars. And scatter plot of the full data set, 42 homes, linear trend. You see this data set here? Can you see it well enough? Yeah. Turns out, and we'll kind of poke around a little bit, there's an interesting outlier up here. You can see that. It kind of messes up the linear trend here. Why? I mean, here basically, we look at 1,000 square foot house.
It's probably an apartment on the top downtown, top of a building.
Lakefront.
Lakefront.
Granite countertops.
Yeah. Basically, you know, it's the most expensive one. It's among the smallest, but it's most expensive. Here is where we as analysts will have to engage higher level brain functions and try to figure out first how to go into the data to find this data point, right? And then try to drill a little bit further and try to explain. What are some possible explanations? Just think. It's one that's trivially easy. Could be wrong. Right? Maybe it is not a 1,000 or 1,200. Maybe it's a 2,200. So it's a keying error. Right? That could be one possible explanation. Well, there's some other ones. I mean, you always mentioned granite countertops and all that. I thought, you know, maybe it's on a 10-acre plot, right? Maybe it's actually not even a house. Maybe it's a farm.
On an oil well.
We've got an oil well, or you know, some
$5 apartment building.
yeah, something. But this would be one, you know. As an analyst, you see something like this, you need to start training yourself to immediately say, what's going on here? And that's just an attitude. It's like, what's going on? Now, it's simple when you have an X, you know, two variables, X, Y plot. Finding these kinds of potential outliers when you have 15 predictors becomes a lot more tricky. But we will help with tools that can do that. Here, by the way, is the code, the R code that produces it. We'll look at it a little bit further. So I read the data into R, call the data set home market value. It's not really a good name for when you sit and type, but it kind of defaults to that. So plotted the data. Now I will want to build a simple regression model where I'm trying to ask R to compute the coefficients that can tell me what this line is. Now I need two coefficients. Remember which one? Coefficients were the B's.
Remember, it's the 0 or the
Now that's the intercept. The B0 is the intercept. And then I need a slope, which is the B1. B0, I forgot to do this.
I know I used to use like a formula like mx plus b. Is that same thing,
Same
right?
thing, same thing. This is just, you know, I got this PhD in statistics, I have to use it for something, and this is how statisticians think. But no, if you have y equals mx plus something, b, it's the same. There are a couple of things going on. You flipped the intercept and this line component, and so basically these numbers are supposed to be the same. The reason I'm writing it up like this, a little bit historic, a little bit when you kind of get deeper into it, this lends itself to write the whole thing out in matrix form. And how much math have you guys had? You know about matrix algebra and stuff? Yeah, you've been exposed to it? So basically what it ends up being here is you can write this out, basically have a y equals a vector here of numbers, and then you can say x equals, and then you have basically there's the B0 coefficients and the B1, and you compute. So x here is a matrix of these B0, B1, B2, B3 coefficients. And then this whole thing, in matrix form, you can compute y's by just doing a x prime x computation, matrix algebra. So it makes it trivially easy to compute. If you don't do it this way, it's a lot more difficult. So that's why statisticians typically will write it out this form, because they kind of been trained to think of this more in a matrix format. Turns out actually for computers too, a matrix format is much better to compute. Completely irrelevant, will not be asked on any test, but it might be something that will simmer in the back of your mind sometime, and you realize that there is actually some very hidden logic to some of this stuff. Now, you don't really have any comparison, and there's with how straightforward this is, and that's intentional. If you were to try to do some of this stuff in Excel, it is the pain in the keyboard and mouse. I mean, Excel is not designed to do this, and it shows. Here, really, to build this regression equation in R, did you recall enough of the intro that you can just arrow is an assignment? Basically says this LM, I call it linear model 1, and LM is a function, linear model. This function, a pattern you can use, and we're going to use this. For those of you that have done programming, we're going to use this again and again and again. Basically, your goal, whatever you want to do, is that you have a function, and then you have this. There's going to be at least two things here. You're going to formula, and you got whatever your data is. So in this case, actually, like this. Result, is a goal, whatever you want to do, a formula, and data. So in this case, I really would like to blow this up if I could, but so this is our result. So our goal in this case is to build a linear model. Our function is, and this function, or this formula, this is how R writes out, or one way of writing out formulas in R. R does something like the following. It says basically our y, and then this is tilde, y depends on x. And this is this way of writing a formula you will see again and again and again. So in this case, we have Lm parentheses y tilde x. This is the formula part. Good so far? And then data equals, and then the data set name. Data equals, I just do a home market value. I'm going to use that, writing out long. But you see how the goal maps to linear model. The formula maps to y depends on x. And the data is basically data equals, in this case, whole market value. This is a pattern that we will use again and again and again. And just to kind of jump back to see that I actually used it also for plotting. The goal is to generate an XY plot. So, and I actually used exactly the same formula. Market value depends on square feet, data equals whole market value, and I get this XY plot. So if you get used to this syntax, at least for what we will do in this class, that will pretty much be 80–90% of what you end up doing in R. A couple of additional commands that you will need to read in data, a couple of things like that, look at data a little bit. But generally, when we do plotting or when we do modeling, we will use this syntax of a goal, a formula, and a data. And the formula being this y depends on x. Sometimes, if you only have one variable, we'll just do a depends on x. And there's more to it too, but very, very fundamentally, that's what we will be doing. So here's this one line that generates the linear regression. And here is part of the reason for why we want to use R and don't want to use Tableau or don't want to use Excel. And that is this output that gives the regression information is written by statisticians for statisticians or for analysts or for modelers. So it actually gives information that is relevant to how we want and what we need. One of my frustrations when I looked at Tableau, and it has this, remember the trend line tool? The trend line tool basically does this. And it computes this line correctly, but it does, if you go in Tableau and look at more of the model information, there are some critical components that R prints out that Tableau doesn't. And we'll get to that. Stop me if you have questions, okay? Trying to do this very, very straightforward and easy, because if you get this, it's going to be so much easier for you in the future. So here's the summary. So this is a how to get this This LM1 is a result object. It knows a lot about the model and the results and all that. So get the summary, get it to print out this, just do summary, parentheses, and the name of the model. We'll go and take a look at what the different parts. There are 4 key things that you need to know initially. Some of this stuff is not important for what we typically will do. Yes?
Are we going to be doing like any sort of lab kind of work?
Not really, since we have the presentation, but then we won't be able to.
Right.
Yeah. So what I will do is I will actually send some R files as part of next week's assignments that you can then source and read into R Studio and basically run them. And I want you.
And it's kind of difficult trying to learn it.
Now what I hope and expect is,
Just constantly getting errors.
Yeah, me too.
This, like that code right there.
You get errors because you don't have the
File.
appropriate library loaded, and you don't have the appropriate data file loaded. So there is a little bit of trickery that comes before this, and I'll actually show you. Okay? So there is a reason for you getting errors if you try to run this. Okay, here. If any of you have R up,
Do we have access to these slides?
yes,
Okay.
yes, I will send them out. What you need to do is you need to do something like install packages.
Yeah, that's what I did see
Okay.
that on the.
You need this. We'll say it's lowercase. Say come on. This install packages mosaic. Enter. And I'm just going to cancel because I have already installed this. Depending a little bit on whether you're using your own computer, while you're using your own computer, yeah. This actually will download not only this one mosaic package, but a lot of other packages too. So it may take a little bit. And then to actually use that package, you would do either
What part of the U.S. would we pick? It doesn't.
go all the way down. There's one in Tennessee.
Tennessee, okay.
Yeah, Tennessee is okay. There's one of these national laboratories, and then you can do library mosaic to actually load, and then it still won't run because you don't have the data set loaded, and I'll show you a little bit later. But that's why you're not getting this code to run. So back to the 4 components that are important for us to know. The first one I want to make sure you understand is when it says this model. Remember that way that we think about it? LM, that's our goal. That's what we're trying to do. In this case, linear model. Formula equals, that's the second part. Dependent variable, or our y variable. The tilde means depends on our x variable. Comma, and then the data equals, and then the name of the data set.
Is that case sensitive?
Yes. Now the other thing, and I'll show you, there are some tricks when you use RStudio. It will do tab completion. So as you start typing something, you can press tab, and if it's unique, it will fill it out for you. But that's what you will see is, I don't particularly like home.market.value as the name of a data set when I'm doing this kind of stuff. So when I write it in, I'll see some code later on. I just call it HMB, all lowercase. That's just, there are some other tricks like that that you eventually will. The reason I kept it like this is I read it in from an Excel spreadsheet. So these dots were spaces in the column names. And these dots here were actually spaces in the variable, in the CSV file name. And R uses spaces as part of its syntax, so it needs to put these dots in there, or periods.
And the square feet, the X variable.
Correct. Yeah. Square feet. Same as this. So this really, you check on this one and confirm what the model is. What this object was created by this call corresponds to this call. If we are looking at this as a regression equation that we want to check on, does it make sense? Does square feet explain anything market value? The first thing we want to look at is the overall check of model goodness. Is the model good or not? And you do that by looking at the F statistic. So here, at the very bottom, last row here, F statistic, and then you get this number. In this case, 45.97. Now, 45.97, what does that mean? As a kind of rule of thumb, if you get F statistics that more than 2, 3 or something, yes, it usually means that the model is significant. But better, maybe easier, is the F statistic. There's also a p-value of this F statistic. And if this p-value is less than some cutoff, remember we talked about p-values? We did talk about p-values, right? Or did we?
I know I learned about them in my statistics course, but...
Okay, so we haven't talked much about p-values. But basically here, if the p-value is less than 0.05 or less 0.1, then it means that the overall model is significant. If that's the case, that kind of allows us to go one step further, so to speak. So a high number here, if it's more than 2, 3, so 45 is a really high number. Or a p-value less than 0.05, 0.1. Statisticians usually have stringent rules about that. We're a little bit more flexible. For us, it says, yeah, that looks good. But it allows us to go to the next check, so to speak, and that's look at adjusted R squared. Remember we talked about the correlation coefficient, the strength of a relationship between two variables? Here it is, R squared. However, in this case, it gives you the multiple R squared, and then it gives you an adjusted R squared. You want to always look at the adjusted R squared. It's not really important with only one variable, one predictor, but what happens is adjusted R squared, the adjustment has to do with number of X variables. So you always want to look at adjusted R squared. In this case, 0.5231 means that this model, this model predicts, or in this case, square footage predicts 52% of the changes in market value. So very often this number right here will be written out as a percentage. So we will interpret that saying, okay, this model, the predictors explain 52% of the variation in the dependent variable. Is that good or bad?
Good.
It is significant. We know that, meaning that it actually there is some predictive value. It's useful. The question is it good or bad? That's a favorite phrase. It depends. It depends on the context. In some contexts, this can be really, really good. In other contexts, this model would not be worth anything, even though it's technically significant, conceptually or for usage purpose, wouldn't be worth anything. So again, while mechanically this is a model that is significant, that is useful potentially, you have to check whether that really holds in the real life. If this were something, if I were a real estate, working with real estate data and all that, I wouldn't just use one predictor variable. I would probably use a large number of them, because the idea eventually would be, oh, a potential seller of a house calls me up and wants a quick estimate of what potential sales price could be. That's the usage. We'll get to that.
I was going to ask you about that. Could you plug in something like a zip code as a factor? It does something to help?
With some tricks, yes. And we will get to those tricks. But this is, again, overall, always remember, adjusted R squared. 52%, so the model explains 52%. So the next thing we then would look at, coefficients. So we have the intercept estimate. So this column is the estimate. This is the actual coefficient. This is the B0, is the intercept coefficient. And B1 is the square foot coefficient per square footage. In this case, since we only have one variable, the square foot, you can see over here, there are p-values as well. You can see that, and then they have these little marks. They're basically saying both of these components of the model help the model. So we get these stars. There are different kinds. There are stars. There are 1 star, 2 star, 3 star. More stars is better in this case. Stronger they help the model. So there's some other stuff here. We don't typically look at. We don't, for our purpose, we don't typically look at some of these other things. The whole degrees of freedom and residual errors. We don't typically use that. If we look at anything, we verify we have the model that we were thinking we're doing. Check the F statistic. Is the overall model usable? Does it work? Does it do something for us? If so, you can go here and look at the adjusted R squared and say, okay, how good is it? This is kind of how good is it? And then eventually, if you say, oh, okay, we can go look at the coefficients. Both the value, the estimate for the coefficient, but eventually also we're going to look at and see whether we might tweak the model by adding or deleting predictors. How am I doing on time? What time is it?
7.
7. You will go over these kinds of output again and again and again. The idea now is to give you first run through. So here's how I actually ended up doing this in R. I used, And here is a typical, what I would do is, I don't call it whole market value, I call it HMV. And I use this function called read file, and then I pointed this to this CSV file. What this does, it creates this data set called HMV. And then here's another command that you'll get all of this. str, it checks the structure. And what it does, it tells us, okay, this is what's called a data frame. I'll give you more information about some of these concepts. It has 42 observations, 3 variables. And then it says, observation, the first observation column basically is house.age. It's an integer, and then it gives us some of those numbers. Next one is square.feet, integer, blah, 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 market.value, integer driven. So this is just verifying what I read in, looking at it, get a feel for it. Things can be integers, they can be characters, they can be something called factors, they can be reals, and we'll get over that. But for now, this is just good. And then, so now, remember what I talked about over here, the kind of generic way of doing things? I want an XY plot. So my goal is an XY plot. My formula, market.value depends on square.feet. And my data is HMV. And R is nice and pops up this for us. You guys remember, you tried to do these kind of XY plots in Excel, right? And it's really tricky to get nice. And that's one of those things too, since R, again, is written by analysts or statisticians for their own usage. There are a lot of stuff happening underneath, trying to make sure that the scaling here is good for graphics, for analytics graphics, and that the labeling makes sense. There's a lot of other things going on like that. If you remember back to how, we say, okay, we read in the data, we want to check the XY plot to verify that there is a linear trend. Then we do our create a regression model. Again, this is just collecting the result so we can use it later. The goal, LM, our formula is market.value depends on square.feet. Data is HMV, whole market value. Then I use the summary function to print out this one. So here, what do we look at? Remember?
The model.
Look at the model. Verify that the model is, okay, formula, market value depends on square feet. Check. Next, what do we look at? What do we look at next?
Coefficients.
R squared.
Yeah, R squared value.
Is the model any good? Where do we get that answer?
Yeah, the F statistic
That's the F statistic.
and the P value.
Yeah, so the P value of the corresponding F statistic. So this is kind of typically where you want to look next. Is this a somewhat big-ish number? Is it? You don't even look, if it's 3 or over, it's good. 45 is a huge, it's very significant. But if it's 2, 3 and above, there are formulas for this, but that's why we have computers. We don't want to compute these things anymore. Computers want to compute, we just want to be able to interpret it. Okay, so we check this one. Yeah, the model is significant. Model is useful, or at least statistically, technically, analytically useful. So now the next question is, how good is the model? So yeah, does the model work? Yes, no? F statistic. Yes. And go next question. How good is the model? Where do we look?
P value.
No, that's
Adjusted R squared.
for how good, we look at adjusted R squared. So adjusted R squared will tell us that 52% of the variation in the dependent variable can be explained by the predictor or predictors. That's typically the way you think about that. And finally, if we say, okay, now is how good? No. What actually is the model specifically? That's when we go look at the coefficients. So in this case, so in this case, what we have, if I just kind of write out this kind of version of it. So our y is what? I'll just call it market value, right? Equals, so what's our B0? Okay, what's the value?
673.22.
Intercept estimate.
32673. 32673. Plus, and in this case, the next one is going to be square feet is our x, right? So what's the coefficient for square feet?
35.
So 35 point something. I'll just use 35. See how we took the coefficients here that are computed and now created our model. What can we do with this model? Well, if you are a real estate broker and somebody calls up and says, you know, I have this house that's like, what do you think I can sell it for? You can ask, what's the square footage? In this case, it's a very, very simple model. Plug in the square footage and computes out, and you get an estimate for market value. In this case, probably would expand and have additional variables. What could be other relevant variables?
Garage.
Whether it has a garage or not,
Age.
age of the house,
Area.
the area,
School district.
school district. I mean, pretty much anything that you can pick up. We will start out by typically using numeric variables here, but there are ways that we can incorporate things like you asked about zip code. You know, you have to make sure that you understand that zip code is actually a categorical variable, not a numeric. You can't claim that, you know, carry 27.511 is less than carry 27.513 being less than carry 27.518.
Doesn't it seem like a lot of real estate people, though, when they come in and give you an estimate, they say, okay, let's see what's sold in your subdivision.
They use another approach. They use the comp.
And that's all they use.
Yeah, they use the comp approach.
Yeah.
However, have you been to places like Zillow and these other Trulia and these? They build these kinds of models basically, and use them when you ask or when they predict the sale prices, market value. Now they build much more sophisticated models, but the basic principle is the same. And then they update them and refresh them. And you know, the actual models and the variables they use and all that, that's proprietary. And it may or may not work. My wife keeps looking at Zillow and disagreeing with Zillow.
Yeah, it's not very accurate.
So, but there are a couple of other things we can pick out of here too. This is a linear relationship. One thing we can say is, if your house is 100 square feet more, what do you expect the increase in market value to be? 3,500, right? If you plug in something like plus 100 here, it's going to increase the market value by 35 times 100, 3,500. Or vice versa, if you have, you know, neighbor has a 2,200 square foot house, you have a 2,100 square foot house. you'd expect this formula at least to suggest that your house is worth 3,500 less. This is applied calculus, by the way. Right? What is this?
It's like a base value or the
This is the intercept. Yes, Kyle is right. It's a base value. It's a kind of a foundational value. You might be stretching it, but you can almost say, hey, if I have a 0 square foot house, basically there is no house there, could this maybe give me an indication of the value of the land? Right? So suddenly now our little regression equation and a little output here, we're starting to understand more from this raw data that we have. We can start to make some very, very educated inferences about what's going on.